So, I am going to talk about something called zero knowledge proofs. So, really I am going to spend most of the time describing what this means, because the combination of words in the title itself is kind of contradictory, right. How can you have a proof with no knowledge inside it? I mean, anything that you are trying to prove is imparting some kind of knowledge. So, we want to formalize a setting in which there is a meaningful way of talking about a proof which does not impart any kind of knowledge. So, let me start with a very simple example. There are two business firms, they deal with two different kinds of products and they are wondering whether to join up, okay, and work together. And the products that they have, they can be used together in a certain way. So, this joining up is, it makes sense only if the numbers that they have match up exactly, otherwise one of them is going to end up with surplus. Okay. So, we have these two companies, let me very unimaginatively just call them A and B, and A has n copies of whatever product they make and B has m copies of whatever product it makes. And what they want is that if n equals m, then let us collaborate, let us join up, else stay separate, stay disjoint. Okay. This is what they would like to do, but they are business rivals. So, they want to decide this thing is n equal to m without revealing what is n and what is m. Without revealing n or m to the other side. Yeah.
This is also called the socialist linear form, right?
There are, yeah, so that is one version of it, and this example in particular I think would match exactly that, but there are many such.
Are we allowed to say that one party says that n is less than 50 years?
They are allowed to do whatever they want, right?
Not the exact value of anything.
No, so here the point is not what do we allow A or B to say. A and B are allowed to say anything. In their own interest, they would like to say things which do not reveal to their rival what is the value of their number. They are free to say, they are even free to say the value of n or m, but they do not want to do that. So, the question is there a way in which they can say things so that at the end of whatever algorithm they execute, they both know whether n is equal to m or n is not equal to m, but neither of them knows the value of the other party. While they execute the algorithm, if
after the end, if finally they know that n equals m, then both of them will know.
So, if it is equal, they will know, and in fact, if you see the setting, if it is equal, it is justified that they should know. If it is equal, they are going to collaborate. So, therefore, it is perfectly valid that they will know that the other person also has this number. But if it is not equal, let us say at the end of it, they figured out that n is not equal to m, does A have more than B, is n greater than m, less than m? Each one does not want the other side to know whether, you know, am I underperforming or am I doing better. They do not want that information to get out.
And n and m are integers, real numbers?
They are integers. So, now in fact, in the particular solution that I will describe, I am going to look at a very restricted case. Let us say that we are dealing with lakhs of rupees, and let us say that there are some nice numbers, say n is 10, 20, 30 or 40, just one of these four numbers, okay, 10, 20, 30 or 40 lakhs of rupees or number of items. So, there are just these four possibilities 10, 20, 30, 40, and now they do not want to reveal the values, but they want to figure out whether they both have the same value. So, there are 16 combinations, right. So, n and m belong to this set. So, how will they go around doing this? They can do whatever they want, but at the end we want this thing to be correctly decided. Okay. Seems like a trick. Huh? So, those of you who have seen it of course know the solution, but if you have not seen any such solution, it seems magical. How can they even do such a thing? So, let me describe one way of doing it.
Are you allowed to use randomization with random numbers in your algorithm?
You can use randomness, but notice that the solution that you are looking for has nothing random about it. Okay. They want to decide this exactly. So, here is one way in which they could do this, and this one way also does not use randomness. Just imagine that you have 4 boxes. So, here I am drawing them as if they are physical boxes. In the digital world, there will be some kind of thing which you code or whatever, but just imagine that you have 4 boxes and the boxes are labeled 10, 20, 30, 40. A has exactly one number, right, of these 4. So, these are all lockable boxes. So, A locks all 4. Okay. While A is locking all 4, and B can also watch. Then what does A do? A throws away 3 keys. The 3 wrong keys. Wrong meaning not corresponding to the number that he or she has.
But what if he lied? What if A lied?
Doesn't matter. Remember what our final goal is, right? So, wrong may not be actually wrong in that sense. Okay. The point is here they are not like fighting against each other, they are just trying to agree correctly whenever the numbers are equal. So, A is going to throw away 3 keys and B sees that A is throwing away 3 keys, A has kept 1 key. And now these are boxes with slits also. So, B inserts slits, slips of paper. You can do that into a locked box also because there are paper slips of paper, and these slips of paper have a minus, 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 plus. The 1 plus is correct for n. This wrong is supposed to be not equal to n, and here the plus is supposed to be at n. Okay. Now A comes back, A opens the box for which A has the key. B is not watching which box A is opening because otherwise B will know the value. So, A opens the box and extracts a slip and shows B the slip. So, at the end of this what happens? Assuming A and B are doing indeed what they were supposed to do, that it is in their interest to try and get a good protocol out of this. So, if A finds a slip with a plus, then assuming A and B neither of them has lied, then A knows that A and B have the same value. Okay. And if A finds a slip with a minus, then assuming both of them have not lied, they know that the numbers are different, but they do not know what the other person's number is, right. But if even one of them lies, then what happens? Then they do not know anything. I mean, maybe A lied and A kept the lock not of his box, maybe A had 20 but kept the key for 30. And then A found a plus there. Then does A know that, aha, I do not have 30, I have only 20, I know that B has 30. To be fair, if A lied, A also has to take into account the possibility that B lied. This can only work if they are both not lying, right. So, that is why I said the setting is not that they are trying to cheat each other. They are actually trying to collaborate and cooperate, and therefore, they will not lie. They are trying to cooperate, but they want to meaningfully find whether the numbers are equal without revealing the numbers if they are not equal. Now, if they honestly follow this protocol, this condition is satisfied, right. So, we are not talking about what happens if they deviate from this. If they deviate from this, then probably neither of them can trust the answer that they get. But assuming that they are both honest, we have now described a way in which they can decide is n equal to m, and at the end if the decision is that n is not equal to m, neither of them knows the other value.
Wait, so if B inserts the slips of paper before A locks out 4?
It does not matter.
No, then how will B insert the slips of paper if A?
So, think of them as letter boxes, you can put in the slip of paper.
B also has a copy of the key, right? B also has a one key.
No, a letter box does not need a key to slip in a.
Right.
So, it is a box in which you can slip in a piece of paper even without opening the box. You can't extract that piece of paper, right. So, it could really be done in any order, but they should not be observing each other when this thing is happening. Like, we should not be seeing which box A opened or which key A threw away, that is all. So, this is an example of a procedure in which two parties are able to come to some decision without giving explicit knowledge about the numbers that they have, except in the case when the numbers match. So, there is one good case, the numbers n and m are equal. In that case, they get knowledge about each other's values, and in all other cases, they get no information. Maybe we should be a little bit more careful. Do they get zero information, or do they get that it is not equal, and that much cannot be helped, right? So, they get some information. If I have 10, I know that you do not have 10. That much information I have got, but that much information cannot be helped if I want to decide this problem. Given that our numbers are different, it could be 20, 30, 40, do I get any indication of which of these three it is more likely, less likely? Nothing. So, in that sense it is fairly close to zero knowledge. Some knowledge is imparted and we would like to say that that knowledge it is necessary to impart it. There is another setting somewhat similar to this, where instead of 2 firms maybe there are n firms and they all have these numbers, and to decide how to proceed next they need to know the sum total of these numbers. The individual values do not matter, but they are all going to operate together in some setting, and once they know the total value of these numbers, then they can decide what to do next. So, they have to know the sum. You have numbers P1, P2, P3 up to Pn, okay. So, P1, P2 and so on up to Pn, and you want to find out P1 plus P2 plus. Let us say we know that these numbers are in the range 1 to 100 or 1 to 1000, we may even know some range for them, but nothing more. So, they have to find out the sum and nobody wants to reveal their number.
We can shuffle the numbers after collecting them.
So, you can put them into a box. Everybody writes their number on a box, puts on a slip of paper, puts it in a box, and then it is read out. And then somebody it's read out and everybody adds. So, does this leak any information? What are the situations where it leaks information?
If all others are 100 and one has 1, then he knows that all others are.
He knows all the other numbers. So, at least one person gets information which was, unlike in the previous case, you can't even say that it is necessary to impart this much of information to get the final sum. In the previous case, it was necessary to know that the value is not 10. Okay, that much information you had to impart. Here it is not like that. It was not necessary at all to reveal anything about the numbers, but there are some instances where that information would get leaked if they write these. So, we are not happy with this solution.
We can maintain a value of 0, and then each person will add his number plus some random number of his choice to that value. Then the second number will do the second person will do the same, and then so on, all people will do the same. Then the first person will subtract his number.
So, let's say the first person says I will give P1 plus R1, where R1 is chosen completely at random.
And they will all do the same. Then first person will subtract his number, other will, and so on.
No, wait. So, P1 plus R1 is done. Then to this you add the next.
To this second person will add P2 plus R.
And do what with that? Send it to the third person.
And
Okay.
then continue until the nth person adds Pn plus Rn.
Okay.
And then afterwards, first person subtracts R1.
So, now this comes back to the first person who takes off. Now just imagine what happens at the n minus 1th position. When it comes back, now you get, so you have P1 to Pn plus R1 plus Rn. The first person knocks off R1, the second person knocks off R2, the second last person knocks off this and passes on a value. The last person knocks off this. Is any information going out anywhere? Only the value of Rn is leaked. So, in this fashion, nobody knows anything about any other number.
By the way, ma'am, I think the protocol discussing earlier, I don't think it can work without a third party. You need a third party to maintain the database of like which.
You can think about it offline. It does, no, it does, the previous protocol does work. You can think about, the previous question, right?
Yeah.
It does work. Okay.
Okay.
But let's come back to that later maybe. Let's move on now.
So suppose everyone knew the total score.
We want everybody finally to know this.
Everybody knows the sum of P1 plus R1 plus P2 plus R2 plus dot. And when P1.
The moment P1 knocks off R1, P2 knows P1. Exactly. So you have to find out where some information is leaked. So the first person knocks off R1.
We maintain a box. In that box, first person writes P1 plus R1 number.
So P1 plus R1, who opens?
Then second person takes it.
So the second person sees what?
The second person only knows, first he knows P1 plus R1.
Okay.
And next time he sees P1 plus Pn plus R2 plus
Okay. So you're right. So there are many variants of, you have a completely different twist to this?
You can put 2 slips into the first box and one slip into the second.
Okay. So there are many variants of this. You can put 2 slips, you can have slips which are put in parallel and then added and so on. Let me just abstract out something a little bit more simply out of this, which has all the important ideas out of what all of you are saying, but it's slightly simpler. The first person sends P1 plus R, okay. but let us say because I want this to be in a cycle, so let us say I go mod m. And then after this each person just adds plus P2 mod m. You need just one random number. The point is each person need not add a random number. Okay. So, each person adds his or her number to what is going on, and then finally it comes back to the first person who removes R. You notice this has all the ideas that you have been talking about in many different ways, different slips and so on. You do not need that. One slip passing around with this will work.
We can also do like we keep two boxes in one.
No, I agree. I am saying that the idea in that solution is already there in this solution. So, this is the simplest version which is distilling out everything from what you are seeing. It's there is this idea that you have to add a random shift to change your number so that it is not visible, and it has to pass on and eventually be removed. Okay, whether you do it with one box or two boxes or n boxes, essentially this is at the core of that. So, this already achieves what we wanted to achieve.
Why do we need the module?
Why do we need the?
Module?
Just so that you do not have two large numbers.
But then don't we lose information?
No, the sum will finally be retrieved here. Okay. So, you come, so for instance, if you knew that all the numbers are in the range 1 to 100, and maybe the first number when it is revealed might give some information, P1 plus R, you want R also to be in a sufficiently large range so that you know something about, you do not know anything about where P1 lies.
This doesn't work for less than or equal to 2 people.
What is less than or equal to 2?
If there are only 2 people, then
No. So, this is for more than 2 people. No, so this will not work for 2 people. Okay. So, for 2 people you do something different. The first problem was more like. So, this is also an example of a zero knowledge, what should I call it? Is this a zero knowledge algorithm? It is an algorithm to compute the sum of n numbers, where there are n different parties who are doing the computation, and at the end of it none of them gets any information about the individual numbers that the other people have. Okay. This needs randomization. This R is absolutely crucial.
This scheme will only fail if everybody else collaborates together and some.
No. So, almost all these schemes will, so these schemes require cooperation.
Right.
So, people are not colluding. We will come to colluding in some other examples, but in this example we are assuming that everybody is honestly following this scheme. They are all interested in knowing that sum, so that then they can go beyond that. So, this is not collusion proof. Okay. So, this would be an example of zero knowledge, but we want to formalize this idea of zero knowledge a little bit more. Let me describe a slightly different example. Okay. So, this different example is, how many of you solve Sudokus? Many of you. Okay. Okay. So, let's take an example of a Sudoku puzzle. So, there are these two siblings. Okay. Okay. So, let's say that let's give them some names. Okay. So, let's say there is Purna, there is Vishal. Okay. Purna says, I have a solution. Okay. And then what does Vishal say? I do not believe you. So, this is one of those I forget what is the nomenclature used. So, one of those extremely hard Sudokus. Some of them say devilish, some of them say fiendish, if you have seen different websites. So, this is a fiendishly hard puzzle, and Purna says she has solved it, and her brother says, I do not believe you at all. How can she convince him that she has the solution? By showing the solution, right? So, one thing which she could do is to say, here is the solution. And if she does that, then of course Vishal's task is completely straightforward, check that it is a solution. Checking the solution is the opposite of extremely fiendish, it is extremely easy task, right? But she does not want to give him the solution. So, this is one of those cases, so this is where zero knowledge is coming in. She wants to convince him, I am smart enough, I have the solution. She does not want to give him the solution because this is a Sudoku which has been discussed already, and people are saying, oh, this is very hard, I do not think you can do it. Once she gives him the solution, he is going to go and brag somewhere else that I cracked it. She does not want to give him that joy. Okay. So, she does not want to give him the solution, but she wants to lord it over him and say, I have the solution. is there any way in which she can convince him that she knows the solution without telling him the solution? Neutral so, do you have a sibling? You and your sibling, do you have a neutral third party? Very rare, you know, most siblings I know the same, you are partial, you know, you always favor. Okay, if you are lucky and you have a neutral third party, great, that's one way to go. That doesn't always work, okay. So, ideally we don't want recourse to this, these two have to sort it out amongst themselves, okay. So, she has to convince him she has a solution, but she she does not want to tell him the solution. So, it seems like an impossible task, but here is one way in which they can do this, which seems to be a bit cumbersome, okay. It is not very easy to actually work it in practice, but as an illustration of a concept, okay. Let's see how it goes. Okay. So, here is our grid and some numbers are already known, okay, and the others are not known. Now, what Purna does is she produces these squares, cardboards, 9 into 9, 81 pieces of cardboard with the numbers written on them. The known numbers in those Sudoku are placed face up, and now the remain. So, she produces these 81 pieces of cardboard, and Vishal can check that indeed there are 9 of each. There is no hocus pocus with the cardboards. Then the ones which are known are shown. So, then the rest are still with her. So, he knows that she is not producing any other thing. She is not using any other cardboard pieces. Now, the other ones, according to her solution, she puts them face down. Okay. So, he can't see the solution, but she places them all and she says this is a valid solution. Now, how can he check?
He can take one row out and
he can take one row out and
check if it has all 1 to 9.
And check that whether it has all 1 to 9. But this will give him some information about the solution. Huh?
No, how he will, otherwise Pona will take all the cardboards in front of him and then shuffle it.
So, that is important, that she has to shuffle them. So, what can happen is Vishal can say, okay, I am going to check whether row 3 has all the numbers 1 to 9. He can't pick up the cards in row 3 one by one. She says, okay, row 3, wait, slide out row 3, shuffle it, here, you check. They have all the numbers 1 to 9, put them back. He may say, I want to check box, second row, third column, box. I want to check that those 9 numbers are all 1 to 9. She will take out just those, shuffle them, give them. How many times does he need to do this to be convinced? Maybe he checks one row and then he says, oh, this was fluke.
27 times.
He can check all 9 rows.
All 9 columns.
She puts them back. After each check, she puts back the pieces. So, what if he asks, first he asks for this row. She gives the pieces from that row, shuffles them, he checks them, gives them back. She again puts them back according to the solution.
What is shuffling?
The way you shuffle cards. Because when you give him the stack of cards, you don't want him to figure out, okay, this was the one which came on top and this goes here, this number goes here. You don't want to reveal the order there. Right? So, you want to mix it up. Sorry, can you speak up a bit? Yes. So these things reveal a little bit of information, right? So there are some cards which are fixed, and because of that you do know a little bit. What do you know about the rest? That you already know if it is a valid solution. You know that the remaining cards have to be the remaining numbers.
So yeah, you shuffle it, give it to him, and then put it back, and then
Exactly. So Vishal asks for cards in a line, in any line, well, it could be a vertical or a horizontal line, or it could be a 3 by 3 box. P shuffles and gives these. Okay. Then Vishal checks and then Purna replaces them. So this is a box, this is a line, this is a line. So Vishal could choose to check a box, a 3 by 3 box, or a row or a column. Are 1 to 9 in a Sudoku. Every 3 by 3 box also has to have the numbers 1 to 9. Every row has, so he can check in a box. She will shuffle this box. He may say, I want to check that this box has the numbers 1 to 9. Then she will take out these 9 cards and shuffle them. Or he may say, I want to check that these 9 cards are 1 to 9.
But after she takes them out, she will have to place them again, right? Yeah. So what if she places them in a different position?
So she could do that.
And then she will be able to pull.
Exactly. So all along what we have discussed till now is, what if Purna really has the solution?
No, but then she will have to know in which order Vishal asked for the rows and so
then she will have to, then when?
If she's placing the cards in a certain manner in first try, and after giving it to Vishal, replacing the cards in another manner.
She can place them back whichever way she wants.
Yeah, so if she is placing it to her advantage, granted she doesn't have the solution.
Exactly. No. So now we are talking about if she does not have the solution, which is also what.
I'm not talking. But then Vishal can say that no, I still don't believe you because you
Yeah, exactly. No. So now this is the analysis that we have to do. So let's look at two different situations. One, Purna genuinely has a solution. In that case, what will she do? Every time she has to place the card, she will place them according to the solution. Every time. I mean, Vishal may ask again and again, okay, now I want to check this row, now I want to check that column. He may even ask for the same row again, some 10 steps down the line, by now maybe she has messed up. And so he may, every time she will place it according to the solution. He can repeat this 10 times, 100 times, 1 million times, she will always pass. Okay. So if she has a solution, this definitely works, and despite succeeding 1 million times, Vishal has no idea what the solution is. Suppose she does not have a solution.
then still somehow she can fool Vishal.
So then she can fool Vishal. What we want to analyze is how likely is it that she will get away. So if she does not have the solution and she claims that she does, what is she really doing? She is cheating. Okay, now this is a probability analysis. This is like kids cheat occasionally in exams, businessmen cheat when they are maintaining accounts, everybody cheats in many different contexts, and what are they doing? They are analyzing the risk. What is the chances that I will get caught out when I cheat like this? We need to do that here. What are the chances that she will get caught if she claims she has a solution and she does not really have a solution? Let's say Vishal repeats this just once, not 1 million times but once. Chances are very small. How small? No, not small. Of course the chances are small. Huh?
Getting caught or not getting caught?
Probability that
Probability.
I think she can place it in such a way that she can basically like 1, 2, 3, 4, 5, 6, 7, 8, 9.
She will always be caught. She will always be
Because
caught.
the face-up cards are shown.
Wouldn't she always be caught because to have a wrong solution you have to have either a number being repeated in a box or a row, or
so maybe there is a number repeated in a row, but Vishal chose a different row to check.
but he has
Then the next time when she places it back, something else. I mean, she could change the solution every time. If she is cheating, she will go all out.
doesn't know which.
She doesn't know.
Out of the 27.
Out of the 20, how many tests are there that Vishal can do? 27. 9 rows, 9 columns, 9 boxes.
At least one will be wrong.
At least one has to be wrong. At least two have to be wrong. Let's say if you are not completely convinced, at least 3. Okay, let's be very conservative. At least one has to be wrong. Everybody agrees. Let's even stick with one.
And then 26 upon 27.
Why does one have to be wrong?
Can all the conditions be correct? Every row has the numbers 1 to 9. Every column has the numbers 1 to 9. Every box has the numbers 1 to 9. That's a solution. Then she has a solution. If she does not have a solution, so let me add this, when she does not have a solution. When she does not have a solution, the probability that she is caught is at least 1 minus, the probability that she is caught is at least 1 over 27, right? Maybe 26 out of 27 cases she hits lucky, Vishal asks for a line which is valid. At least 1 out of 27 times she will be caught. But that's too little. Why would Vishal be convinced that she has the solution? Suppose he does not catch her out, that only means that it was by fluke, she was lucky. Now she is going to repeat this, he is going to repeat this k times. K may be as large as 1 million. Okay. So now let's write this. What is the probability that P is not caught? Is not caught after K trials. After K trials.
Less than equal to 26 by 27 days per.
Excellent.
I mean, it should be at least 5. At least 5.
At least
5 should be incorrect.
no, I'm just looking at this. The probability that you are not caught is at most 26 by 27. Actually, it's even less than 26.
At least 22%.
Yeah, so that number, this inequality is still valid, right? I mean, instead of 26, you have something even smaller. That's fine. And K times this has to happen, but each trial is independent. Each time she is replacing the solution, alleged solution, and doing this. You can use your calculator if you want and figure out that by the time K is something like 20, already this thing is very tiny. So if Vishal does this 20 times and every time it still turns out that all the conditions are satisfied, then he'll say, okay, man gaye. I believe that you have this. I still don't know the solution, but I believe that you have it.
I don't think 20 is good enough. 26 upon 27 is 27 is about 1%.
So there is some number that you have to calculate.
Yeah, just a 30% chance that
So how much do you want it to be?
you want it to be like hundreds or
If you want it to be 1 in 100, then you choose K. So you can choose your confidence level. I want to be, I want to give Purna not more than a 1% chance of winning, or I want to give her a not more than a 0.02 chance of cheating and winning. Depending on how much confidence you want, you can change the number of trials. Remember, increasing the number of trials makes no difference whatsoever if she is genuinely in possession of a solution. If she has a solution, you can make K 1 million, 1 zillion million, whatever, she will still pass. So she cannot complain at some point saying, oh, you are making K too large, this is too hard for me. She has no, if she says that, then already he can say you are lying, right? So you can make K as large as you want until you are confident enough, okay? So this is one way in which she can convince him that I have a solution, and she has given no information whatsoever about what that solution is. This would be an example of a zero knowledge proof. So what was the theorem and what was the proof? Okay. So here in this setting, the theorem that was being, normally when you say proof, you have in mind a theorem, no? So the theorem is that Purna has a solution. This is for a specific Sudoku setting. This is the theorem. And what was the proof? The proof was not a kind of proof that you are used to, the kind of proofs that you have encountered in your geometry. So, you know, you would have seen proof that these two triangles are congruent under these conditions, proof that this angle is cos of this is equal to sine of that plus some. This is not that kind of a proof where you are writing step by step by step and then verifying that each step follows from the previous step. This proof involved some interaction between these two people. They had to I will give you a little bit of information about the proof, you will check that, you will ask some questions about it, I will give you some more information in response to your question. So there was a very interactive style of verifying a proof. Okay. So interactively verify. That is one component to what we described. The other component is that randomness was absolutely essential. If there was no randomness, if Vishal was not going to check this thing randomly, but is always going to check the second row or always going to check the third column, then I mean Purna can trivially cheat, no? So it was important that Purna doesn't know a priori what line, what box Vishal is going to check. So randomness is absolutely essential. And the third feature about this proof was that no knowledge of the solution was imparted. Yeah.
Instead, if at each place Purna keeps 27 cards of the mix, the cards should be such that they should be of the same this, and then like there should be a 27 stack of same number, and then it should have a lock that if unless you unlock it, you cannot separate the 27 pieces. When you unlock it,
So that's a different solution. What you're describing is a different solution. Does it change any of these features?
yeah, it doesn't need randomness.
It will need it in one of the two settings. It will need it in one of those two. You have to formally argue that when she has a solution, she will always pass, and when she does not have a solution, she will definitely not pass?
Yeah.
No, I don't think
No,
so.
see, we will say a stack has all numbers equal to same. All numbers
then what is the check being done?
Yeah, and then it has a lock, means Purna will keep it this way, and then she will open the locks in front of Vishal, and now Purna won't touch anything. So now Vishal will ask, and they will take the top of each time. And
Yes,
they
yes.
will shuffle.
So this does not read randomness, but this in fact introduces a different level of problem which is much more subtle, which is, so what you're saying is that Purna keeps a stack of 27 cards. The top layer from each of these stacks is what will be picked out if he wants to choose a row. The second one is what if he wants to choose the next row, and so on. What is the proof that across these stacks they are consistent with one solution?
No, the stacks are like, should be bought from some store or something which
No. I'm glad that you cannot think of how you can cheat this way, because we don't want two devious minds here, but yes, you can cheat. We'll discuss it offline. No, let's discuss it later. There are more devious things that you can do this way. Or either she can do more devious things, or he will fail to check a correct proof. Let's discuss it later. But this solution, if everybody is convinced with, then I would like to move ahead to another idea, which
All the cards will be hidden from Purna.
initially, yes.
Yeah, so what if the solution is not for the specific Sudoku, but she made one Sudoku and hide the card?
No, so that Vishal is allowed to open the cards which were part of the original Sudoku and see them. That can be done. And that will not change the properties we saw earlier, which is that with a correct solution she will never fail, and with a wrong solution she will be caught with high probability. These are the two important properties that we want. These will not change even if those fixed cards are revealed. Okay? And the third property that we want is that information about a solution is not revealed. That is not revealed by revealing cards which were already fixed in the initial puzzle. So you can reveal those cards and nothing changes. Okay? But yeah, there could be other ways also of dealing with this, and there could be other ways of cheating depending on how you deal with this. But this is one setting. Let me now, I want to introduce one more idea, and then again through another puzzle which involves these three features: interaction, randomness, and nothing being revealed, and maybe that will allow us to get a better feeling for how to formalize these things. So this is often described as, if you go later on, if you go to, or even now in parallel while you are listening to me, you could be on the net. If you go to Wikipedia and ask for zero knowledge proofs, one of the examples given is this thing which is called Ali Baba's cave. Okay? But this is a strange cave. It has, this is a mountain, and there is a tunnel which goes around like this, and there is a block here. There is a magic password. And if you give this password, then this whole thing is a sliding rock door which moves aside, and you can go from here to here. So let's say that we have again two people here. Prabhat knows the password. Okay, and there's one more person. Vijaya. Vijaya wants proof. Proof of what? Proof of the fact that Prabhat has the password. Okay. There's one very easy way in which Prabhat can prove this to Vijaya. Come, walk with me. We'll go around this way. We'll reach here. I'll say the password. This will open. You will see for yourself. So when the password is said, this thing opens, stays open for a few seconds, and then closes again. So it's not that he can leave it open and she can go and then come back. So she can go with him. He can open it, show her, all is well. She knows he has the password. She also probably knows the password. So maybe the password is something that has to be said aloud, or maybe you have to touch some specific parts of the, if you have seen Lord of the Rings, then you know that there are such passwords also. So maybe he does want to convince her that he has the password, but he doesn't want her to know the password. So then he can't take her. So then how can he do this? Okay, so that is, she can stay here. And what P does is to go this way and come out this way.
Why do someone else first and she opens?
I think there should be two rows for that.
If somebody else has the password, then at least Vijaya knows somebody who has, Prabhat knows somebody who has the password, which is good enough. Prabhat has a way of opening that door, right?
I didn't say that. Like if someone else has the password and he opens it before Prabhat.
No, so she can go in and check that the door is shut, come out, and say now you go this way and come out the other way. Okay. So that can be done. So Vijay is standing here waiting, Prabhat goes in, comes out the other way. Vijay is completely convinced, yes, you must have had the password, otherwise you could not have done this. So this would also be an example of a zero knowledge proof, in the sense that having done this, Prabhat has not revealed to Vijay any information about the actual password. In this case, the solution is the password. But if Prabhat actually has the password, he will always succeed in this test. So it is in that sense, it is a zero knowledge proof. It is not completely zero knowledge in another sense, which is that maybe Prabhat wants to convince Vijaya that he has the password, but he doesn't want anybody else to know whether or not he has the password. Even this fact, the fact that I have the password, is sensitive information, nobody else should know. Now, if there is anybody else here who is waiting with Vijaya and watching this happening, they see Prabhat going that way, coming out this way, then that person also, so a random observer, an arbitrary observer who is also standing there at the entrance now knows that Prabhat has the password.
Vijaya can go to the other side of the wall and he can go to the other side and then.
But an observer could be with Vijaya. So any observer who is with Vijaya will also know that Prabhat has the password, and we want to avoid this. Okay.
So if Vijay wants to know that, she should come and come observer.
Okay, so let's see. Prabhat wants Vijaya to be convinced that he has the password. Prabhat wants no one else to know that he has the password. Is there any way at all of doing this? Okay.
Like they both agree of something. She stands there. He goes inside, opens the gate and throws this thing to the other side. Comes back from here. They both go there and check if that thing is present there.
That would work. It would have the same problem that the previous instance had, which is that an observer who is with Vijaya.
But can the observer be with Vijaya and also somewhere else, or is there only one observer?
So the you could think of the observer as the world at large. It is like a little bit like, with this Aadhaar verification. I want that person to know that this is indeed me, but nobody else should know. Then the observer is not one person. The observer is like anybody else in the whole wide world. In particular, it could be that a spy has attached a microchip camera to Vijaya's sleeve or something. Vijaya doesn't even know that the observer is there and the camera is relaying information. It should not reveal information about this. Now this is asking for a bit too much, no?
That is a little advanced.
That is too advanced. Huh? Something like that we want to do, but we may not need a quite Diffie-Hellman. No. So we may not quite need that. That is one possible way of. But let me describe another way which uses randomness. So Vijay is here, and so incidentally there was Purna and Vishal, and there is Prabhat and Vijay. This P and V are important. P is the prover, V is the verifier. The prover is proving I have a solution. The verifier is verifying, do you really have a solution? It could be any names. On the Wikipedia, it's usually Peggy and Victor or something like that. P and V is important. Okay, here is another way in which they can do this. Prabhat goes in from any way. Maybe Prabhat goes in from A. Vijaya sees Prabhat going in. Then Vijaya flips a coin. Okay. So she makes a random decision. She can physically flip a coin, or she can randomly pull out a number from her head. And maybe pulling it out from your head in some sense is better because a camera cannot see you do that. So let's say that the coin, the random decision says A. So she calls out A, Prabhat comes out from aisle A. Prabhat goes in again, she randomly calls out B, he comes out from B. So he goes in, and then after some time she calls out one direction and he has to come out from whatever direction she says. Okay. Now, if he has the password, he can always meet this. Whatever she calls, he can come out that way. If he does not have the password, he cannot, sometimes he can, sometimes he cannot, right. So again we need to do a probabilistic analysis. Yeah. So this is still not the full solution. So if P has the password, then the probability that P succeeds is 1. And if P does not have the password, then the probability that P succeeds is how much? 1 by 3? 1 over 2, 1 over 2. Half the times, because there are 2 possibilities, one of them you will succeed, one of them. If you repeat this k times, then this is going to be raised to k. Okay. Now we have to come to the observer. Okay. So now I admit I am going to change the definition of what the observer is allowed. So this is not a completely all pervasive observer, but what is the observer seeing? The observer, let us say the observer is with Vijaya at the entrance to the cave, and the observer says that she calls out some direction, he comes from there. She calls out some direction, he comes from there. So he sees this, the observer sees this, and the observer says he is getting this right every time. Obviously he has the password. So he comes out and the observer nabs him and says, I know you have the password. And Prabhat turns around and says, how do you know? You know, it was set up between us. So the view that the observer sees of she is calling out something and he is responding to it correctly, this view could have been generated by a prover verifier pair where neither of them had the password. So now how does the observer know which of these 2 situations actually happened? The observer does not know. Now this is zero knowledge in a completely different sense. Okay. So this is what I want to write down here. Observer cannot distinguish between 2 situations. Between P has the password observer sees that this fellow Prabhat is always coming out from the direction which Vijaya called out. It suggests that Prabhat has the password, but it could equally well be that Prabhat and Vijaya suspect that there is an observer, a spy watching, and they have carefully set up this game to fool. This is now a double spy game. It could be like that also. So as a suspicious observer, how can you convince yourself that indeed Prabhat has the password? Actually you can't. You can only convince yourself about this if you see the coin tosses that Vijaya is doing, because the coin tosses are truly random. If you can see access to that true randomness, then you would probably be convinced about whether or not Prabhat has the password. Without that, you cannot. Yeah.
So if like Vijaya always calls out the direction that we went in, then that is how they can collude.
No. Okay. So for this to be a good test, maybe Vijaya should not even see the direction in which Prabhat goes in, right? It's like hide and seek.
How can they collude there?
Oh, they might have set this up well before they reached anywhere near the cave. Collusion, there are always a million ways. Okay. So this is like hide and seek. Maybe she does not even see which way he has gone. Okay. I mean, if she sees which way he has gone, then why will she use randomness? She will just call the other side, no? To check that he can. Yeah, so therefore this will only work with a certain type of observer. I agree. It will not work with the completely all pervasive observer, but so somebody who cannot go past that entrance to the cave, cannot see which way he has gone in the beginning, cannot be convinced about this. Okay. So this is a little bit better than the previous solution. Some notion of secrecy about this solution has been maintained, but it's not completely foolproof. Now you can make this more and more fancy, more and more sophisticated, and get around more and more of these questions. So let me repeat what are the requirements. Okay, no, not repeat. I never wrote them in this form. So now let me write down. So what are the requirements of a zero knowledge proof? So in each of these cases, there was a certain theorem to be proven. In this last case, in the case of the cave, the theorem to be proven is Prabhat has the password. That is the statement, right? So a zero knowledge proof of any theorem, it has 3 requirements. So the first requirement is completeness. What do we mean by completeness? If the statement is true, then an honest prover must be able to convince an honest verifier. We saw that this was certainly the case for Sudoku, this was also the case for the cave question. Okay. So, this is condition 1. Condition 2 is what we call soundness. If statement is false, then any prover could be cheating. I mean, there is no question of an honest prover here, right, because the statement is false. Then any prover cannot convince an honest verifier. Maybe here I need to say except with tiny probability. I mean, these things are randomness, there is some 1 in a million chance. So, except with tiny probability. And then there is a third condition. So, the third condition is the zero knowledge condition. An observer gains no knowledge about the, not just observer, well, even the prover. Prover gains no knowledge. Of course, the prover knows the proof. Observer and the verifier gains no knowledge except that the statement is true. Okay. So, these are the 3 requirements of a zero knowledge proof. It should be complete, it should be sound, and it should not leak out information. And all the examples that I did were, very informal play, puzzle kind of examples. Let me give you one formal example, and we won't do a full analysis. I'll just leave it with you to think about it. So, here we are going to start with a problem which is hard. So, you started off this morning with complexity, and you saw that there are some problems which are NP complete. It's very hard to solve them. But typically NP complete problems, and in fact this is more or less by definition, they may be hard to solve, to find solutions to, but if somebody gives you a solution, it is easy to verify that it's a solution. The solution can be verified in polynomial time. So, here is a candidate, here is an example of a problem which is NP hard. It's NP complete. Okay. Do you know what these cycles are? Hamiltonian cycles?
Cycle that visits every vertex, every edge once or something.
Not every edge, every vertex. So, a Hamiltonian cycle in a graph is a cycle which visits all the vertices exactly once. So, if you have a graph on n vertices and it does not have all the edges in it, some edges are there, some edges are not there, and you want to go around visiting in whatever order you want, you should never repeat a vertex and you should end where you started. Not all graphs have Hamilton cycles. So, the question here is, given an input graph, does it have a Hamiltonian cycle? This is NP hard. Okay. So, now the setting is there is an input graph G, and now the prover claims G has a Ham cycle. The prover has to convince the verifier that this graph has a Hamiltonian cycle and I know that Hamiltonian cycle. But the prover does not want to tell the verifier what the cycle is, because that cycle is probably the password to some setting, and the verifier is just some doorkeeper's security guardsman. You should not know the password, that is too sensitive information. So, he has to be convinced that you know it so that you can go through, but he should not get access to that actual solution. So, in order to do this convincing, the prover is going to use another problem which is also in NP, and this other problem is roughly like this. So, graph isomorphism. So, here there are 2 graphs. So, for example, maybe this is one graph, numbers 1, 2, 3, 4, 5, and here is another graph also on the vertices 1, 2, 3, 4, 5, but the graph looks very different. Okay. And here at least pictorially they are drawn like this, but typically these are going to be graphs with hundreds of vertices and they are given as an adjacency matrix, and now you are asking, are they really the same graph? Are these graphs really different? What is the big difference? I mean, you just rename 3 as 2 and you do some renumbering of the vertices and they are the same, they are both 5 cycles. So, in general I am going to give you 2 big graphs and I ask you, are they the same? Can you renumber the vertices of one graph so that after you renumber, then it becomes exactly the same as the first graph? This problem is reasonably hard. We don't know whether it is NP complete, but we don't know of any p time algorithm for it. Any polynomial time algorithm is not known. But if I give you a solution, you can quickly check. What do I mean when I say give you a solution? I can give you the way to renumber the vertices.
I don't think it can be NP complete since
It is not known to be NP complete.
No, it's not exponential times in quasi polynomial. Papa got a
Yeah.
So it can't be NP.
It can still be.
It should be NP complete.
It could. It could still be. So as of now, we don't know that it is NP complete. It's not one of the hardest problems in NP perhaps, but at the same time, we don't know that it is in P. Okay. So what would a solution to this be? If I claim that these two graphs are isomorphic, I can give you the way to renumber them. You renumber accordingly, and then just checking whether the graphs have become the same is easy. Okay. So this is an example again. It has these typical NP properties that coming up with a solution seems hard, but verifying a solution seems easy. This can be used in an interactive zero knowledge proof for Hamilton cycle. How would we do this? Okay. So here's, remember the problem is Hamilton cycle.
We can like permute the vertices in the graph.
You can permute. Okay, but what will you do with the permuted thing? So here's what the prover does. Okay, the prover does the following: randomly permute G, permute the numbering in G. Okay, so you renumber the vertices of G in some way, and then you get H. Okay, so H is this new graph. And let us say that you have a drawing of H, or maybe you write out the adjacency of matrix of H on some large chart paper or whatever, you have it there. Now, what the verifier is allowed to do is the following: randomly pick one of these two tests. There are two tests that the verifier could ask to do, but the verifier is allowed to do only one in one trial. Okay. So one test is show that G is isomorphic to H. I would write it this way: isomorphic to H, meaning that they are essentially the same except for a numbering. If the verifier chooses this test, then the prover responds, prover shows H and shows the renumbering. Okay. So this is one test that could be done. The other test that the verifier could do is to say, show that H has a Hamiltonian cycle. Okay. Then P shows a cycle in H. Now stare at this for some time and see. If P knows a Hamilton cycle in G, P can always pass these tests, whichever test is asked. Whichever way P chooses to permute H, she can always give the specific renumbering that was used to produce H, she can always produce the cycle. There was a cycle in G, after renumbering the cycle has shifted around, but there is still a cycle here. So whichever of these two tests we ask for, the prover can give a solution. But suppose the graph does not have a Hamilton cycle at all. The prover has to choose an H. The prover does not know a priori which test the verifier is going to ask for. So the prover may say, I think that the verifier will ask me for the isomorphism test, so I'll give an H which is indeed random, indeed a random permutation of G, and does this, and then with the prover's luck the verifier says, show me the Hamilton cycle. But if H was indeed a permutation of G, H also will not have a cycle. So because the prover does not know in advance what is the question to be asked, the prover will not be able to game this system. The prover's chance of winning a test if there is no Hamilton cycle is half. The prover cannot pass in both cases. One test has to fail, and which test is being chosen randomly. So remember this first line here where I have said that the prover randomly permutes G to get H. This is what the honest prover does. When G has a Hamilton cycle, this is what the honest prover does, and the honest prover convinces the honest verifier. When G does not have a Hamilton cycle, we can't say what the prover will do. That prover is anyway cheating, could do anything, may be producing an H which is not a permutation of G at all. Okay. Whatever the prover does, in one out of these two cases, the test will fail and the prover will be caught. You repeat this some 10 times, 20 times depending on what confidence you want, and you will know that the prover is cheating. What information about the Hamilton cycle in G is leaked through this? Nothing. Because at the end, even in this situation, what is the prover showing the verifier? A cycle of length n. But a Hamilton cycle is a cycle of length n. So the fact that you have shown a cycle of length n doesn't mean anything. No information about a cycle in G is revealed. So this is a classic example of a zero knowledge proof for a NP complete problem. There are many NP complete problems for which we do have zero knowledge proofs like this unconditionally. There are some other NP complete problems for which under some assumptions we know that there are zero knowledge proofs.
This scheme, it is like secure against collusionary. I mean, malicious actors or whatever. Even if one of them is evil or whatever, it will still be secure.
So P could be as evil as, so that is not evil. The evil and all you are talking about in.
Like lying or whatever. Malicious.
So that is a requirement of a zero knowledge proof. In a zero knowledge proof, if the statement is false, a cheating prover should not be able to convince a verifier. Not just this protocol, that is a requirement of the zero knowledge proof. A cheating prover should not succeed except with very tiny probability.
And if suppose graph isomorphism became easy to solve, then this would become quite insecure, right?
Yes. So this this depends on the fact that we don't know how to solve isomorphism. Yeah. So there are many other such examples where you can play around and see how to reveal the proof of that you know the proof of a statement without actually giving the proof. And I would encourage you to try and figure out more such instances and figure out the zero knowledge ways of convincing the other person. I'll stop here. We can discuss more later also if you like. Thank you.